SwayamPrabha. Digital India. Educated India.
Hello, welcome to the last lecture of this course, which is on where we will continue on the topic, same topic that we were discussing in the last lecture. So, in the last lecture we have seen that for a fixed free column, which was perfect column, and which had uniform cross section. So, we have found out that this is the generalized solution for the transverse deformation. So, this is for any boundary condition. So, we have seen that this is basically the solution to the differential equation d4p by dz4 plus p into d2v by dz square is equal to 0. So, this was the equation that we had derived for any for a perfect column with any arbitrary boundary condition, and the generic solution was this. Now, by imposing the boundary condition for a fixed free column into this generalized solution, we have found out that the solution or that is going to be mu is 2n minus 1 pi by L, and Vz is going to be a 1 minus mu z, where a could be any arbitrary constant. Now, from this two expression we can say that mu square, which is p by ei, and that is equal to 2n minus 1 square pi square by 4l square, p critical. So, therefore, for this we can say that p critical is nothing but 2n minus 1 whole square pi square by 4l square. So, this is therefore the critical buckling load for a fixed column. So, this is the critical buckling load for a fixed free column. Okay. So, similarly along with this we have got that this is the buckling mode or the shape buckling mode for fixed free column. Now, if we therefore see that the first critical buckling load is therefore going to be pi square, sorry, there is an ei here, pi square by 4l square into ei. So, that is the first buckling load that we get. So, we are going to get that as p square into pi square ei by 4l square. So, the second critical buckling load is going to be P critical 2, which is going to be 9 pi square by 4 L square into E I, and so on. So, therefore, if I draw the column, if I draw the column for the first buckling mode, this is what we are going to see. P critical 1 is going to be pi square E I by 4 L square, and the first buckling mode V Z is going to be A 1 minus cos 2 n minus 1 pi z by 2 L. So, therefore, if I try to plot it, the first buckling mode is going to be like this or like this. So, this is going to be represented by Vz, which is going to be some arbitrary constant A 1 minus cos, sorry, it should not be 2 n minus 1. So, this is going to be pi z by 2 L. So, this is going to be cos pi z by 2 L. So, this is the solution. So, this is similar to the pin case. So, for pin case, our critical buckling load was pi square L square into E I, where here the critical buckling load has reduced further and it is pi square by 4 L square into E I. So, this and the buckling mode also, the shape of the buckling mode has also changed, where in the previous case it was just sin mu L, whereas here it has become cos 1 minus cos pi z by L. So, when L is z is equal to 0, then this is going to be 0, and when z is equal to L, this is going to be 1. Now, similarly, the second buckling mode can also be drawn. So, if this is the undeformed column, the second buckling mode can also be drawn in this form, either this or this or this, as we know that the actual deformation is non-unique, but the shape is unique. So, because of this A factor here, we have non-uniqueness property, which we have discussed in detail for a pin case. Here also we have this non-unique condition. So, this is the second critical mode. So, P critical 2. So, this is the second buckling mode. So, the P critical 1 is P critical 2 is going to be 9 pi square E I by 4 L square, and V2Z is going to be some arbitrary constant 1 A minus cos 3 pi Z by 2 L. So, similarly, we can find out the other higher order buckling mode. So, we have done this example in detail for a fixed free column. We can also do it for other boundary condition, that is fixed or fixed beam, pinned and so on. So, the methodology that has to be followed is exactly the same. So, now let us move on to a concept which is called effective length of a column. Now, this is a very commonly used terminology used in the column buckling problem. So, what is meant by effective length? So, we have seen that for a pin column, the critical buckling load P critical is pi square E I by L square, the first critical load. Now, for a fixed free column, we have seen, we have just derived it, and we have seen that P critical, for that the first critical load is pi square E I by 4 L square. And for though we haven't calculated it, we can always calculate for a fixed column, and we will see there using the same technique that we have just discussed, that P critical is going to be 4 pi square E I by L square. Now, this thing can actually be written as pi square E I by L E square, where L E is called the effective length of the column. So, irrespective of the boundary condition, the expression for critical buckling load can be written as pi square E I by L E square, where the L E is the called the effective length of the column, which is used as a common terminology in case of column buckling. So, now therefore, for a pin column, L E is equal to L, whereas for a fixed free column, L E is equal to 2 L. Whereas for a fixed column, L E is equal to L by 2. So, this is what is meant by effective length of a column. So, there is one more thing that I want to discuss at this point, that we can see that the critical buckling load or the capability of a column to withstand buckling load depends strongly on the boundary condition. As you can see that the critical buckling load of a fixed column is almost 16 times more than that of a fixed free column. Therefore, it is very important to clearly know what is the boundary condition of a column when we are doing buckling analysis. Now, in theory, it is precisely known what are the boundary conditions, but when it comes to practice, it is very difficult to precisely tell or accurately tell what are the boundary conditions, because though if you try to make it a fixed column, there might be some manufacturing or building error by which we do not get complete fixity at one end, and there is some amount of non-constraint at the fixed end. That will strongly influence the buckling capacity or the compressive load bearing capacity of that column. So, in real life, in practice, one has to be very careful while identifying the boundary condition of a column in order to accurately or design it for the buckling load. Now, with this we have come to an end of the theory of column buckling. We will now do some example problem to understand the theory that we have discussed in more detail. So, let me do this example. So, we have this structure where we have a beam whose one end is pinned or one end is simply supported or pinned and the other end C is free. At the midpoint of this beam at which is B, another member BD is connected, which is connected at the fixed end, and it's making an angle of 30 degree with the horizontal axis. Now, there is a moment m0 being applied at the free end or the end C of the column. Now, we need to find, the statement is that find the critical value of the applied moment m0. So, we need to find out m0 so that none of these two members of this system undergoes buckling. So, now in order to analyze the structure, let us first draw the free body diagram. Now, if we draw the free body diagram, the ABC so we can identify that this member is a two force member. Right, because it is connected only at the two end and there are no intermediate force or moment acting on this member. So, this certainly is a two force member. So, using this idea, if we say that this is R1, the two reactions at A, R1 and R2, and the reaction at B is going to be R3. And there is this applied moment m0 at C. So, this is the free body diagram of the portion ABC. Now, the free body diagram of the two force member is just going to be, so this is B and this is D, and the two force because it is a two force member, there are R3 and there is R3. Okay. Now, let us try to find out what is R3 or what are the reaction forces R1, R2 and R3. Now, if we take moment about A, taking moment about A, we can say that R3 sin 30. So, the vertical component is going to be R3 sin 30. So, we can write that R3 sin 30 into L is going to be m0. So, that implies that R3 is going to be m0 by sin 30 into L, which is 2 m0 by L. Now, this is a pin joint which I have forgot to mention. So, if this is a pin joint, then we can say that the critical buckling load for BD can actually be written as, can be written as pi square EI by L square, because it is a pin-pin joint. So, my R3 needs to be less than this. Now, what is R3? R3 is in turn 2 m0 by L, and that needs to be less than pi square EI by L square. That implies that m0 needs to be less than pi square EI by 2L. So, this is the one criteria that we have got. So, this is my equation 1. Now, let us look into the portion A, B, C. Now, critical buckling load for A, B, C Now, if we look into the portion A, B, C, so if I just quickly draw this, so R1 is going to be R3 cos 30. So, which is root 3 m0 by L. Therefore, what we have is, on the axial side we are going to have R1 and we are going to have R3 cos 30, which is equal to R1. Okay. So, therefore, we can say that the critical buckling load for this portion is only for this portion, L, because from B to C there is no axial load acting. So, this is A, this is B to C. So, the load is acting. So, we can say that axial compressive load is acting only on AB. Therefore, my critical buckling load is going to be P critical for ABC. Therefore, is going to be P critical for AB, which is going to be pi square EI by L square. Now, therefore, R1, which is equal to root over 3 m0 by L, has to be less than pi square EI by L square. Now, from this we can get that m0 has to be less than pi square EI by root over 3 L. So, this is the second criteria that we are going to get. So, this is the second criteria. Now, if we see criteria 1 and criteria 2, we have to take the lowest of these two. Therefore, we can say that the lowest value of m0 is equal to pi square EI by 2L. So, therefore, this is the answer that we are going to look for. So, this is how we get the answer for the problem. Now, let us move on to a second problem quickly and let us try to solve that. So, let us take a fixed free column. So, let us take this case where we have a fixed free column of uniform cross section and of length L. At the free end, an axial compressive load P is applied to the column through a rigid link, so that the P has an eccentricity of E from the centroidal axis. So, the point of application of P is making a distance E from the centroidal axis. So, we can say that the load is applied at a distance E from the centroidal axis. And we need to find the tip displacement. Now, if we intend to do so, how are we going to solve the problem? So, we have to write down the equation of motion, which we know it is d4v by dz4 plus nu square into d2v by dz square, okay, and that is equal to 0. So, this is the governing differential equation. Now, the solution of this equation is Vz, which is, we have derived this earlier, Bz plus C cos mu z plus d sin mu z. Now, what are the boundary conditions here? The boundary conditions are going to change because of the eccentricity. So, if we write down the boundary conditions, we say that V0 is equal to 0 and dV by dz at z equals to 0 is going to be 0. And we say that m, which is EI d2v by dz square at z equals to L, now no longer is 0. That is going to be the moment produced by P due to the eccentricity E. So, P into E. So, this is the important change that we are going to see. Now, so this is the most important change that we are going to see. And then the third point, which is D3V, that is shear force, which is D3V by dz cube plus nu square dV by dz is going to be equal to 0. So, this is going to remain as is. So, this one, so at z equals to L. So, this one and this two are going to remain same. Now, if we impose this condition to the generic solution and we solve for this, we will say that we will get Vz as m0 by P cos mu L into 1 minus cos mu z. In turn, m0 can actually be written as P into E by P cos mu L into 1 minus cos mu z. Now, these two are going to get cancelled. So, eventually, I am going to have Vz, which is going to be E by cos mu L into 1 minus cos mu z. Therefore, the tip deflection can actually be written as del, which is V of L, which is E by cos mu L 1 minus cos mu L, which can further be simplified as del, which is V L is equal to E sec mu L minus 1. So, therefore, this is the answer that we are looking forward to. I have skipped the details, but the details are very straightforward as we have discussed that in detail in the last lecture. So, what is most important is to identify this boundary condition and then the solution becomes simple. So, this brings us to the end of the course. Thank you immensely for attending this course and going through the lectures. I hope it will be of benefit to you. Thank you.